today. And so they've got a new website. It used to be a really long name. Now they've called it symotter.org. So that's the place where you can go to learn all about the symmetry elements and to assign point groups. They don't go as far as we do in terms of learning about the direct product tables and how to use them and the character tables and how to use them. But if you can't get the point group, you can't use all that other stuff either. So this will at least get you to the point of finding the point group for a molecule. This has a nice little flow chart that you can go through to find the point group, but eventually you'll want to work up to where you don't even need the flow chart, that you can just look at a molecule and compare it in your mind to a molecule that you know, and then you'll be able to assign the point group. For example, water. This molecule here is what we would call a C2V molecule, and we'll learn what that means, okay? But then you also have something like dichloromethane. Dichloromethane. It's also C2V. And so that's sort of the Jeff Foxworthy thing. If you think dichloromethane and water are the same, you might be a pea chemist. Right? You would drink water, you'd never drink that. But in terms of symmetry, they're the same. They're both C2V. Okay, so that's one of my arguments. So we'll go on to this symmetry tutorial. And this will walk us through the symmetry reflection planes, inversion centers, proper rotation axes, and improper rotation axes. Just check on this. Okay, we're good. And so let's go through. They're up here on the left side. You have identity, reflection, inversion, proper rotation, and improper rotation. And we're going to use these example molecules down here. So let's go ahead and start with the first one, identity. We have a couple of different options for molecules. But this is a molecule that has no symmetry elements except identity. There's no rotation, there's no reflection, there's no inversion in this molecule. This is what we would call an asymmetric molecule. So putting the A in front of symmetry negates the symmetry. So it's asymmetric. There's no symmetry in that. That's a vocabulary word. You might grab that one. You know, symmetric and asymmetric. A meaning no symmetry. And so the only thing that you have on this is the identity operation. There's really no animation because how do you animate nothing? Simplest animation ever. Okay. Let's go on to reflection. So here's ammonia. Can you look at that molecule and see the threefold symmetry? Right? It's got three parts that are identical. They're what angle from each other? Just looking down at this from the top down on the molecule, it's 360 divided by 3. So that'd be 120. So the angles between those hydrogens is 120. That would be rotation. Let's look at reflection. So here are the sigma V planes. Oops, it's slow. So be patient. And then we can animate all three of them. So that's reflection through that plane. That's reflection through that plane. So you see there are 3 different reflection planes in this molecule. And then this one. And so in the character table, you'll sometimes see that there's 3 sigma V's, or sometimes they'll separate them out. They'll say sigma V prime, sigma V double prime, sigma V triple prime. And so they'll just put primes on them just sort of to designate them, and then if you were to draw them, you might designate them with the primes as well. Let's look at water. So we've got that reflection plane, we can animate that, and the hydrogens reflect into each other. Where do you think the second reflection plane is?
Down the middle.
Yeah, down the middle of the molecule. It doesn't really do much to animate this one because it's the left half of those atoms reflecting into the right half of those atoms. Now, but that reflection plane still does something to the electron cloud. It takes the front half of that electron cloud and the back half and swaps it. So that is an important symmetry operation. And then benzene, we saw these last time. We have all of the sigma D planes and the sigma B planes. Let's animate some of these. This will be much more exciting. Now everything's staying in the plane when it reflects. It goes straight across. Let me rotate the molecule up and we can see that reflection. Let me get rid of some of these. So we'll just look at that one and animate it. The thing is, it's very clear on the website. What your job is to make it clear in your own head. To look at benzene and say, okay, I can see how these atoms would reflect into each other. That's the trick. And so instead of just playing with this website and having fun with it, you know, oh, look, this animation, look at that. Try to get that into your head where you can look at a molecule and see it. Because what you're going to have to do is take benzene drawn on the board. And if it's an organic chemist, they draw it like that. They don't even put the hydrogens on it. And you need to be able to see that reflection plane. So there might be a reflection plane right here, which is what we've got shown. And so this carbon connects to that carbon, this carbon to that one, that carbon to that one, and then the hydrogens that are not shown also connect to each other. So one way you could think about this, if this is hydrogen A and that's hydrogen B, this reflection connects A and B or just swaps the labels on them. Okay. Now, what if I have a chlorine here and a hydrogen there? Then I've lost that reflection plane. Okay, so that breaks the symmetry. So just because it's a benzene molecule, if I break the symmetry by putting a different type of atom on there, then it's no longer benzene. It's a different kind of molecule. It has different symmetry properties. So the things that reflect into each other have to have the same identity. They have to have the same element, same either hydrogen or carbon or what have you. If I wanted to maintain that reflection plane, I'd have to put a chlorine on that side too. Is everybody clear with the reflection planes? Yes?
Do isotopes break symmetry?
Good question. There's different kinds of spectroscopy, like rotational spectroscopy versus electronic spectroscopy. And since isotopes don't change the charge on the nucleus, the electron cloud symmetry stays the same. But the moments of inertia, which depend upon the masses for rotation, would change. So it's a great question because it's still the same element. And so it still has the same charge. And so the symmetry of the electron cloud would not change. But the symmetry of the rotation of the whole molecule would change. It might be a small effect, it might be a big effect. I mean, if you're changing hydrogen to deuterium, you're doubling that mass. And so that has a pretty large effect. But going from chlorine 35 to 37, not much effect. So you would have very little change. So I guess it's the worst kind of answer that you ever want to a question is it depends. You know? Right? But I'm not saying that because I don't know the answer. I'm saying it because it depends upon the size of the molecule and whether it's rotating versus it's the electron cloud, which depends on the charges. And I can say for sure it doesn't change the electron cloud because that's based on the nuclear charges. And all you're doing with isotopes is adding neutrons, which are neutral. So they don't change the charge, but they do change the mass. And I guess the most dramatic case would be hydrogen, doubling it to go to deuterium, or even crazier, tripling it to go to tritium. And so tritium is pretty rarely used because it's radioactive and pretty highly radioactive. But there are isotopes. You know, you can use tritium in some extreme cases, and see dramatic effects on rotation. So it depends. Let's look at let's see, that was reflection. Let's look at inversion. Now this is tetrachloroplatinate. So platinum in the middle, 4 chlorines. It's just a big square. Okay. So the inversion center is right in the middle. You can animate that, and everything goes through the center of mass. Now this is a particular case where the inversion center actually, there's an atom at the center of mass, platinum. But there does not need to be. So let's change this back to a hydrogen. So the center of mass for benzene is right there in the middle of the molecule, and there's no atom there. Okay, so that you don't have to, reflect through a particular atom, you reflect through the center of mass. In fact, that point right there is the point of the point group. So when we talk about point group symmetry, they're talking about symmetry around the center of mass of the molecule. And all of the reflection planes, the inversion center, the rotation axes, they all go through that point. So if you can stand on that point and look around the molecule, you can visualize a lot of the symmetry. Let's look at benzene. So here's the inversion of benzene. The inversion center is right in the middle, center of mass, and then everything goes through that center of inversion, and it goes the same distance to the other side. So if I stand on this hydrogen, I look through the point of symmetry, and I end up over here. Now, it's because of my crappy drawing that it looks like I should go over here, but it really should be over here. Okay? And so I just wasn't as careful as I needed to be. But you can see if you draw something poorly, sometimes it can be hard to see the symmetry elements. Okay? Because it looks like that hydrogen should go through that point of inversion and end up over here, and there's nothing over there. Okay? So it's much better on the board, on the screen. And then ethane. So we're looking down the carbon-carbon bond on ethane. I'm going to rotate it up so that we can see it a little better. Okay. So that's exactly how I would draw ethane. Let me see. So I've got the carbon-carbon bond. And you draw as many atoms and bonds in the plane as possible. So those are all the bonds and the atoms that are in the plane. And then you draw the wedges and dashes. So over here, we've got one coming out and one going back. And up here, got one coming out and one going back. So can you see, this is how you draw it on your paper, and that's what you're representing up there. Where is the inversion center? Let's not use the software yet. Let's draw it on here. Where's the inversion center in this molecule? Exactly. It's going to always be the center of mass. So this right here is the inversion center. And so this hydrogen will go straight through that inversion center to that hydrogen. And this one in the back would come through there to that one in front. I'm going to draw that as a wedge. Okay. See how that works? This one's in the back. It comes through the inversion center to that one. So it connects all the atoms on the opposite sides of the molecule. So if this is carbon B and this is carbon A, they're connected as well. So let's animate this and we'll see what I've tried to draw on the board. So everything goes through the center of mass and comes out on the other side. So that is what we call staggered ethane, because if you look down the end of the molecule, those dihedral angles are staggered. And so the hydrogens are kind of in between each other. What about eclipsed ethane? How would I draw that? I would have all of those bonds that are in the plane, they would be on the same side of the molecule. Does this one have an inversion center? No. It does not. How do you know so fast? Yeah, if this is in the plane, it's going to end up in the plane. So it would go through the center of mass here, and end up over here, but there's no hydrogen in the plane over here. These hydrogens are in front and back. So this one does not have an inversion center. So there's a big difference between staggered ethane and eclipsed ethane. This would be eclipsed ethane. If I were to look down the carbon-carbon bond, this hydrogen would eclipse that hydrogen. It's like the moon and the sun. Okay. And so eclipsed ethane has no inversion center. The staggered ethane does. So that's inversion. Does everybody understand? Pretty comfortable with inversion? Okay. Let's do proper rotation. Let's use the same molecule. So here we're looking down. Can you see the threefold symmetry in that molecule? If I rotate it 1/3 of a turn, 120 degrees, then the hydrogens will move to the next spot where there's a hydrogen. So here's the C3 axis coming straight out of the board. Let me tilt it a little bit so you can see that axis. Okay. And then we're going to animate that one. Okay. So it looked like it went 2 spots, but what we're seeing, watch this again. Right there, the top one is sort of eclipsing the bottom one. So let me tilt it up and you can see what I'm talking about. Okay. So it's going 1/3 of a turn. So the top ones are going to the top ones, the bottom ones are going to the bottom ones. Fantastic. Okay, now this has it shows 2 C3 operations. One is a C3 and the other is a C3 minus 1. It's raised to the -1 power, okay? And that just means go in the opposite direction. So let's animate that one. See, it goes to the right. Or clockwise. One goes to the counterclockwise, one goes clockwise. Now this has some C2 axes. What do I mean by C2? That little subscript 2. What is that telling you?
0.180.
Yeah, so it's whatever you're dividing 360 by. So 360 divided by 2 is 180. And so the C2 axes are 180 degrees. It can't be down this axis because if I rotate that 180, this hydrogen doesn't have anything to rotate into. There's no hydrogen over there. So that can't be the C2 axis. That has to be the C3 axis. But if I tip this up, can you see the C2 axis right here? Again, mentally, you've got to be able to look at that molecule and say, yes, if I rotate that 180 degrees, the hydrogen's going to the hydrogens, the carbon's going to the carbons. So let's look at those. Let me turn the C3 axis off. And there are the C2s. So I'm just going to pick one of them. Good, got the right one. See, that's a 180 degree rotation. And there's 3 of these. Because you've got 3 hydrogens pointing off. So one of them rotates this way, the other one rotates this way, and the other one rotates this way. So they just spin around, hydrogen to hydrogen, carbon to carbon. And here's the last one. So as I've drawn this molecule, let me swap my hydrogens down here. So we have that axis coming right out of the board. That's a C2 axis. And you can see that this hydrogen would be connected to that one. The front one stays in front, the back one stays in back. And the carbons also swap. So every element changes position, and it has to be the same element on both ends. If this was a nitrogen, then, and this a carbon, then it would lose this rotation. So that's the rotation axes. The little subscript is the divisor, so 360 divided by whatever that subscript is. And then the exponent, you can have +1 or -1, just tells you rotating one way or the other. The reason we use it for the C3 and not the C2s is whether I go clockwise on the C2, these hydrogens change if I go clockwise. The same hydrogens change position if I go counterclockwise. So I only have one C2 here. How is it that I have two C3s? Let me turn that one on again. And that's because if I go counterclockwise, this hydrogen goes over there. But if I go clockwise, it goes over to a different position. So there really are two different motions with the C3 because you're exchanging different labels on the atoms. You're moving them to different positions. Okay. That's proper rotation. Let's do improper rotation. Staying with methane, if I wanted to get this hydrogen not to exchange with this one, or that one, or this one with a C2, how could I exchange it with that one? So how could I get this hydrogen to move to that position? I can't get there with a C3. I can't get there with a C2. There's one other operation that I could do. It's called rotation reflection. So I'm going to rotate this one out of the plane. So it's going to rotate this way, only 60 degrees, not 120. So I'm going to rotate this way. I'm drawing kind of a wedge so that you show it's coming towards you. And then I'm going to reflect down. And I'm going to hit that hydrogen. So instead of going a third of a turn, I'm going to go a sixth of a turn. 1/6 of a turn, and then reflect down. And I'm going to reflect through the plane that contains the center of mass. So that's a horizontal plane. So I'm going to reflect, I'm going to rotate and reflect. So let's animate that one. Let me tip it up so it looks like what's on the board. It's an S6 axis. It's 1/6 of a turn and then a reflection. So it'll go 60 degrees and then reflect down. So it's a little slower this time, but that's okay. So 1/6 of a turn and then reflect down. And that way I can swap the top hydrogens and the bottom hydrogens. We rotate and reflect down, and then the molecule looks like it did before. That was probably the most difficult to see, but they're easy to see whenever you flip it on its end and look this way, is you can see, okay, I've got a staggered situation. Whenever you have a staggered situation and all those elements are the same, you have an S axis. So you can look at that and go, okay, I have an S, and it's 1/6 of a turn instead of threefold. You see the threefold symmetry with just a proper rotation. You see the sixfold symmetry with the improper rotation, or the rotation reflection element. So that's probably the most difficult one to see, but it happens in all these cases where you have a staggered rotation of two identical end pieces. So what do you think it is for ferrocene? Let me draw ferrocene for you. Oh boy, that red doesn't erase. Is it Sharpie? Okay, so ferrocene, you have a 5-membered ring at the top, an iron in the middle, and then a 5-membered ring on the bottom. And just look at these 5-membered rings. There's sort of a flat piece there and a point on this end. It's kind of an arrow pointing to the right. A flat piece here and an arrow pointing on the left. They're identical rings on top and bottom, and they're staggered. Okay, so we know it's a 5-membered ring, so you have a proper rotation, a C5, 1/5 of a turn. But then 1/10 of a turn will put this right above this carbon here. And so it would be an S10. So a C5 and an S10. An S10 will rotate this out front and drop it down to there. And then S10 squared, so doing it twice, we'll move it back up here. And S10 cubed, then, to the 4th power, 5th, 6th, 7th, 8th, 9th, 10. When you do an S10 10 times, you get back to where you were. Same with an S3, an S6. You do that 6 times, and this hydrogen here will bounce down. So S6 to the 1st power, 2nd power, 3rd, 4th, 5th, and 6th power, you're back to where you were. So all of these symmetry operations, you can do them multiple times and get back to where you started. The S6 minus 1 just goes the opposite direction. They really slow things down. There's the reflection. Let's do it one more time. So that's sort of a tutorial on all of the different symmetry elements. So those are elements. Just like we have fundamental elements, you know, everything's made of carbon or hydrogen or whatever. The symmetry of a molecule is made up of different elements. Well, these are not periodic table elements. These are symmetry elements. There's 5 of them. And those are the 5 that we've gone through. Okay. We use those, we identify those, we answer questions about those, and then we arrive at the point group. The point group describes all of the symmetry in the molecule. You don't have to identify every symmetry element to get to the point group. You really just have to look how it reflects and rotates, and maybe inversion. The point group will seldom, if ever, I don't know if it ever does, seldom depend upon the improper rotation or the rotation reflection. So if you're struggling with that one, it's okay. You can still identify the point group in 98% of the molecules without doing this one, but there may be 1 or 2 cases where this is the thing that breaks a tie. Right. So let's go on to going further, the point groups. So we have a little description of what it means in terms of point groups. And then we had this symmetry challenge, these flow charts. So let's do ammonia. That'll be an easy one to start with. Okay. And so the first question, we haven't really talked. Okay, the first question is asking about an infinite reflection axis. So let's discuss what that means. This is a trick too. If you can't get it off, you put fresh on there. The solvent dissolves it. Okay. Look at that. Pro tip. So we looked at threefold symmetry. What if I have something like carbon dioxide or carbon monoxide? It's a linear molecule. Looking down the end, I mean, I've got rotational symmetry around that molecule. And if I rotate it, 180, it still looks the same. What if I rotate it 60? It looks the same. What if I rotate it 1 over infinitieth? Still looks the same. And so I could take 360 and divide by infinity, and that would be a C infinity axis. Right? So I could just rotate it, 1 infinitieth of a rotation, and it still looks the same. And that's the first question in this point group. Basically, you're asking the question, is this a linear molecule? Right? Does it have a C infinity axis? Is it linear? So you should be able to identify if the molecule is linear or not. Okay? All the atoms have to be on the same axis for it to be linear. That's not asking if it's a long molecule. Right? It could be a bunch of carbons bonded to each other with double bonds, and then at the end you've got a couple of hydrogens sticking off the axis. It's a long molecule, but it's not linear because of those hydrogens. Okay? But acetylene, carbon triple bond to carbon, hydrogens still on the same axis, that's a linear molecule. So we asked this question, does the molecule have an infinite rotation axis, yes or no?
No.
Good. Does this molecule contain 2 or more unique C3 axes?
No.
It has a C3 axis, you can see that. It's threefold symmetry, but it's asking if it has 2 or more. Okay, unique ones. That's the word 2. So a C3 positive one, a C3 minus one, those are 2 C3 operations, but it's the same axis. Okay, so that's the difference. It has 2 operations of C3, but it's not a different axis. A different axis will point off in a different direction in space. Okay. So it does not contain 2 or more unique C3 axes. What molecule would? Like something like methane, right? Where you've got, you could look down this carbon hydrogen and rotate it 3 times, or you could look down a different hydrogen and rotate it 3 times. So methane would be a great example of something that has a bunch of C3 axes, definitely 2 or more. But this one does not, so we would say no. Okay, select the highest order proper rotation axis. So that would be looking down this one here. And then it's asking if there are present, let's see, select the highest proper rotation axis. If any are present, so C3, select, okay. Are there 3 C2 axes perpendicular to the highest order axis? So is there a C2 90 degrees to that? No, there's not. For a C2, you'd have to be able to rotate the molecule, and so a hydrogen would have to come up on top. Think about that ethane. You know, there was a C2 90 degrees to the C3. So this is asking, is this molecule like ethane? Okay, and it's not like ethane. It doesn't have a top and a bottom that look the same. Okay. So our 3C2, no. So we say no to that. Does this molecule contain a horizontal reflection plane? What is horizontal, though? Let's talk about that. We identified that this molecule has a C3 axis that goes like this, okay? And that's the only only axis it has. Ready with me on that? That, by definition, is going to be the z-axis. And we're going to use the right-hand coordinate system. So x cross y gives z. So your finger is x, this middle finger is y, and the thumb is z. So that's the right-hand rule. Notice if I use my left hand, x, y, z, then I have a different x and y. X is over here, y is there. So we're using the right-hand system. X, Y, Z, it goes counterclockwise when you draw your coordinate system like this. So X is coming out the front, and Y is off to the side. So the ZY plane is the plane of the board. The ZX plane is coming out straight at you. And the XY plane is the horizontal plane. That's defined as the horizontal plane. Z is up. This is the horizontal plane. Is there a horizontal reflection plane? No. So we would say no to that one. And we're almost out of time, but that's okay. Does it contain 3 vertical planes? Yes, it does. And that'll get us to this. We've determined the point group as C3V. So that's how you use this flow chart. And you can print the flow chart off from Blackboard. And you can have the paper copy here, and you can do the tutorial. So that's your homework. Do these molecules on this. And to pick a different molecule, you just come over here and click one. And you've got all these different molecules to do. Yeah, and you can do screenshots of the ones you do. So just doing molecules and point groups this week is, you know, and 9 points is I mean, that's all you're doing for credit, but you got to do way more than 9 molecules. That's just what we have on the table for each week. Okay. Yes.
How is 1 point for each molecule?
Yeah, 1 point for each molecule. So you do at least 9, but I think you should probably do 20 or 30. And in the lab, you're doing a bunch, yeah.